Hello, everyone. In this video, we're going to look at example 2 in section 14.3. In this example, we're going to start becoming familiar with the differential of a function. All right, so let's get started by reading the situation. So here we're told that in a room, the temperature is given by T equals to F of xt in degrees Celsius, where x is the distance away from a heater in meters, and T is the elapsed time in minutes since the heater has been turned on. So now we're told that a person is standing 3 meters from the heater 5 minutes after it has been turned on. So before continuing, let's go ahead and draw a picture of kind of what the situation is looking like. And by picture, I want to draw a graph. So here we'll represent the distance that the person is from the heater. So that's x in meters. And then here we'll represent the time that's passed. Okay, so what we're considering is someone who's 3 meters away. So maybe 3 is here. And the time that has passed is 5 minutes. So maybe we're here at 5. So this is the point 3, 5. So at this point, 3 meters away, 5 minutes later, there's some temperature of the room. Okay, and so what we're told is that 1, the temperature is increasing by 1.2 degrees per minute, and 2, walking away from the heater, so if you fix time and walk away, the temperature decreases by 2 centimeters per meter. So notice that we're looking at the change of the temperature with respect to time. The temperature is increasing by this degrees per minute. And the temperature is also changing by meters. So depending on how far away you are, the temperature changes. Now we want to estimate how much cooler or warmer it would be to be a little closer, 2.5 meters from the heater, and have 6 minutes pass. So where does that look like? So now we're over here at 2.5 and up to 6. Let's draw that point here. So this is 2.5 meters away, 6 minutes later. We want to know, how is this temperature different? So to do this, we're going to need to consider how our temperature changes both as we get closer to the heater, so moving in this direction, getting closer to the heater, and as time passes, so as T increases. All right, so let's get into some calculations. So what we want to do is find that change in temperature. So we can write delta T, that's going to be the change in temp of the room. So we need to consider, again, the change of the temperature from just moving closer to the heater, so the change of x with respect to the change of x. And we also need to consider the change in temperature by having time change, so change of T. So let's consider the change of temperature in each direction separately. So first, we can consider the change of temperature by moving closer to the heater. So the change of temperature. Well, we were given that the temperature is increasing by 1.2 centimeters per minute, but also walking away from the heater, the temperature decreases by 2 centimeters per meter. So we know that the change of our temperature just by moving away or closer to the heater is going to be -2 degrees Celsius per minute, or meter, rather. I'll write out meter so it's a bit more clear. But that's per meter, and we haven't gone a whole meter. How far have we gone? Well, from 3 meters to 0.5 meters, we've gone -0.5 meters. So our change of time and location is -0.5 meters. So just by making that change, walking to the point that's 2.5 meters away from our heater, meaning walking closer to our heater, we should see that the temperature will change by -2 times -0.5, which becomes 1 degree Celsius. So this says that we are going to get, the temperature rather, is going to get warmer as we move closer to the heater. And in fact, the temperature will increase by 1 degree Celsius as we move a half a meter closer. So we should think, does that make sense? Yeah, probably makes sense. Half a meter closer, gets a little warmer by 1 degree. So I'm going to clean this up a bit and actually not have equals 1 degree Celsius, but put that underneath here because we still want to compute the change in temperature in the t direction as well. All right, so let's go ahead and look at that then. So now we're considering moving 1 minute later. So we want to ask the question, well, how does the temperature change as the time changes? And so we're told that the temperature is increasing by 1.2 centimeters or degrees Celsius per minute. So here we know then that we have a 1.2 degrees Celsius per minute now change in the time direction. And our change of time, well, from 5 to 6 is 1 minute. So canceling out minutes, we see that the change in temperature just from the change of time is going to be 1.2 degrees Celsius. And we can ask, does this make sense? Well, yeah, as the heater, the longer it stays on. So as we move forward in time, the hotter it should be. So then this total change of temperature is going to be 2.2 degrees Celsius. So that's how much we're going to change if we instead were at a position 2.5 meters away 6 minutes later. So to summarize, we see that the temp increases by about 2.2 degrees Celsius from the points 3.5 to the points 2.56. And again, the context here, 3 is meters away, 5 is minutes after the heater's been on, and similar down here. So what we just did was compute how our function f changed as we changed x a certain amount and t a certain amount. So this process can actually be done more general. And one thing to note is what we're actually computing here. So this -2 degrees Celsius per meter, that's actually the way that f changes with respect to x at 3.5. And then here, this 1.2 rate tells us how f changes in the t direction at 3.5. And then what we've multiplied by is the change of the x and the change of the time. So doing this computation that we just did and adding them together gives us the total change of the function from the point where we started with to the point where we get the change of x and change of time. So what we just computed is a differential. So let's look at that definition, the differential of a function. So if we're given a function, we call it z equals f of xy, and the differential with notation, we use df or dz at a point AB is given by this expression. We have df is equal to the derivative in the x direction at AB times dx plus the derivative in the y direction of at AB times dy, or the change in y. And so conceptually, this differential represents the approximate change in the output of f if x is changed by dx and y is changed by dy. So graphically, going back to our example here, we saw the change of temperature from, or of the situation from the point 3.5 to the point 2.56. And that is called this differential of a function. So in the next example, we're going to see how to compute a differential for another situation.